Hello, welcome to the course SJPHY3 BO3 Electrodynamics 1. I am Dr. Benoy Anand from St. Joseph's College, Irinjalakuda. The contents of this course is taken from Introduction to Electrodynamics by David J. Griffiths. In today's lecture, let's discuss the first chapter of Griffiths' vector analysis. I'm sure most of you are familiar with the concept of vectors. Vectors are quantities which have both magnitude and direction. For example, velocity, acceleration, force, momentum, etc. On the other hand, scalars are quantities which have only magnitude and no direction. For example, mass, density, charge, etc. Now, in the convention followed by Griffiths, bolded letters represent vectors and ordinary letters represent scalars. Let's now get familiarized with some of the basic vector operations. Start with addition of two vectors. If you want to find sum of vectors A and B, place the tail of vector B on the head of vector A. So A and B are arranged in tail to head manner. Now the third side of this triangle will give you A plus B. Similarly, if you want to find B plus A, place tail of vector A on the head of vector B. Now B and A are arranged in head to tail manner. Now the third side gives you B plus A. A plus B is same as B plus A. This is known as commutative properties. A plus B plus C is equal to A plus B plus C. This is known as associative properties. And A minus B is same as A plus minus B. Second operation is scalar multiplication. If you multiply the vector A plus B with a scalar A into A plus B equal to A into A plus A into B. This is known as distributive property. Next is dot product of two vectors. Suppose you have two vectors A and B arranged in tail to tail manner. Let theta be the angle between them. Then the dot product of A and B, known as A dot B, is defined as AB cos theta. So this is a product of the magnitude of vector A with the projection of vector B along the direction of A. Now a dot product is commutative. A dot B is same as B dot A. It is also distributive. A dot B plus C is equal to A dot B plus A dot C. Now from the definition of dot product, you can easily make out that when A and B are parallel, A dot B equal to A into B. Here theta equal to 0, cos theta is going to be 1. So when A and B are parallel, the dot product is same as the normal product. On the other hand, when A and B are perpendicular, cos theta is going to be 0 and A dot B equal to 0. Similarly, A dot A, dot product of a vector with itself will give you square of its magnitude. Now if you take this particular configuration, here vector B and vector C are arranged in head to tail manner, meaning the third side A will be sum of B and C. So you can write C equal to A minus B. When you take dot product of C with itself, C dot C equal to A minus B dot A minus B, which you can expand as A dot A minus A dot B minus B dot A plus B dot B. Now C dot C equal to C square, which is equal to A square plus B square minus 2AB cos theta, which is the famous law of cosine. So this is a consequence of the dot product of two vectors. Another vector operation is cross product. So cross product of two vectors A and B is defined as A cross B equal to AB sin theta n cap, where n cap is a unit vector perpendicular to both A and B. Now first thing you notice is that unlike the dot product, which was a scalar, this is a vector. Now the direction of the cross product is given by the right hand rule. Now if you want to find out the direction of A cross B, place your right hand in the direction of vector A. Now curl it towards vector B. The direction of your thumb gives you the direction of A cross B. So if you follow this rule, you find that A cross B gives you a direction into the page, whereas if you look at B cross A, the direction of the thumb is out of the page. Now assume that you have an arrow. When the arrow goes into the page, you see only the tail of the arrow, which is represented by a cross. On the other hand, when the arrow comes out of the page, you see only the head of the arrow, which is represented by a dot. So A cross B is represented as a cross and B cross A represented as a dot. As you have already noticed, the directions of A cross B and B cross A are opposite. So you can write B cross A equal to minus A cross B. So cross product is not commutative, but it is distributive. You can write A cross B plus C as A cross B plus A cross C. And from the definition of cross product, you can easily make out A cross A equal to 0 because sin 0 equal to 0. Now geometrically, what does the cross product mean? So you have two sides A and B, and theta is the angle between them. And if you take modulus of A cross B, this is the area of the parallelogram generated by the sides A and B. You can represent a vector in terms of its components. Now, to define the components, you need a coordinate system or a frame of reference. You have two options. One, choose a Cartesian coordinate system like here, where the three axes are x, y, and z. Alternatively, you can choose a polar coordinate system depending on the symmetry. Now we will discuss the polar coordinate system later. For now, let's take the simple Cartesian coordinate system. Now as I said, it has three components x, y, z. Now a unit vector in the direction of x axis is taken as x cap or I cap. Similarly, you have y cap and z cap in y and z direction. So x cap, y cap, z cap are known as the basis vectors, and you have three components in these three directions. So the component in the x direction, you call it as ax. Similarly, you have ay and az. So these are the components, and the capped vectors are the basic vectors. So the total vector is written as a sum of three components. You can write vector A equal to ax x cap plus ay y cap plus az z cap. Now if you want to add two vectors, you need to add the like components. So suppose you have vector A and B, write them in the component form and add the like components. You get A plus B equal to ax plus bx x cap plus ay plus by y cap plus az plus bz z cap. Now if you want to multiply a vector with a scalar, you need to multiply each component. So scalar A into vector A equal to ax x cap plus ay y cap plus az z cap. Now to calculate the dot product, you need to multiply the like components and add them. Since a dot product of a vector with itself will give you square of that vector. We are talking about unit vectors here, so square of the unit vector is 1. So x dot x cap is same as y dot y cap equal to z dot z cap equal to 1. Since x, y and z are perpendicular to each other, x dot x cap dot y cap equal to x cap dot z cap equal to y cap dot z cap equal to 0. So this follows from the definition of the dot product. Now if you want to find the dot product of two vectors a and b, so this is equal to ax x cap plus ay y cap plus az z cap dot bx x cap plus by y cap plus bz z cap. So you need to multiply the like components and add them. So this gives you ax bx plus ay by plus az bz. Similarly, a dot a equal to ax square plus ay square plus az square, or magnitude of a is square root of ax square plus ay square plus az square. Similarly, if you want to calculate the cross product, you can use the determinant method. So a cross b equal to determinant. In the first row you have the basis vectors, in the second row you have components of a vector, and the third row you have components of b vector. So you know how to expand this. So this is equal to ay bz minus az by into x cap plus az bx minus ax bz into y cap plus ax by minus ay bx into z cap. Now from the definition of cross product, x cap cross x cap equal to 0. Similarly, y cap cross y cap equal to 0 and z cap cross z cap equal to 0. Now if you follow the right hand rule, x cap cross y cap will give you z cap. Similarly, y cap cross z cap will give you x cap, and z cap cross x cap will give you y cap. So this follows from the definition of the cross product. Now similarly, you have triple products. There are two types of triple products. One is scalar triple product defined as a dot b cross c, and a vector triple product which is defined as a cross b cross c. So let's talk about the scalar triple product first. Now you have three vectors a, b and c. They form a parallelepiped. Now if you look at the physical meaning of this definition, B cross C gives you the area of the base parallelogram. Now you need to take its dot product with A. So this gives you a cos theta component, which is the height of the parallelepiped. So you are multiplying base area with the height, which gives you volume of the parallelepiped. So modulus of A dot B cross C gives you the volume of the parallelepiped generated by A, B and C. Now you can write the scalar triple product as a determinant. So in the first row you have components of A vector followed by components of B vector followed by components of C vector. And you can expand this and find out the value of the triple product. Now there are different ways you can write this triple product. So A dot B cross C, what you need to do, you move C to the left and shift A and B to the right. So you get the similar triple product. So A dot B cross C is same as C dot A cross B. Once again you shift B to the extreme left and move C and A to the right. So you get this is equal to B dot C cross A. So all these terms are equivalent. Now let's define the vector triple product A cross B cross C. this is equal to B into A dot C minus C into A dot B. Since the vector products are not commutative, A cross B cross C equal to minus C cross A cross B. If you follow this definition, this is equal to minus A into B dot C plus B into A dot C. Now you can take any complex vector products and simplify that using the triple product and the double product. For example, if you take cross product of 4 vectors, now you can reduce this using the triple product formula and finally you get the result. This is equal to B into A dot C cross D minus A dot B into C cross D. So any complex vector operation you can simplify using a triple product or a double product. Now, when you start learning about electrostatics or magnetostatic, you will realize that the most important thing to understand the electric field associated with a charge is to identify the position or the location of the charge. So for this you need a position vector. So for defining a position vector you need a coordinate system. For now let's stick to the Cartesian coordinate system. So if you call the position vector as R vector, it has 3 components x, y, z. So you can write it in the component form as R equal to x, x cap plus y, y cap plus z, z cap. Now the magnitude of the position vector is given by square root of x square plus y square plus z square. And the unit vector in the direction of the position vector is given by vector r divided by its magnitude, which is equal to x cap plus y cap plus z cap divided by the magnitude square root of x square plus y square plus z square. Now if your particle makes a motion from coordinates x, y, z to x plus dx, y plus dy and z plus dz. Now this infinitesimal displacement can be written as displacement vector dl equal to dx x cap plus dy y cap plus dz z cap. Now when you talk about electrostatics, you have a charged particle and an electric field associated with it. Now the charged particle is the source of the electric field, so you can call the position of the charged particle as a source point. Now in some other point you want to measure the strength of the electric field. So this point is known as the field point. So you have 2 different points here, a source point and a field point. And these 2 are represented by 2 separate position vectors. So to define the position vector, let's invoke a Cartesian coordinate system. And the position vector of the source point, let me call it as r prime. And the position vector of the field point, let me call as r vectors. So these are 2 separate vectors. And the distance between the source point and the field point is another vector known as this r vector. So we have 3 different vectors here and you should understand the relation between them. As you can make out, r prime and r vector are arranged in head to tail manner. So r vector equal to r prime plus r, or the distance vector r equal to r minus r prime, which you can write in component form as x minus x prime x cap plus y minus y prime y cap plus z minus z prime z cap. Okay, so having understood how to define position vector using a particular coordinate system, let's now try to see how we transform vectors when we move from one coordinate system to another coordinate system. Now, suppose you want to study motion of a particle, or if you want to identify location of a particle, you need a coordinate system. Now, the choice of the coordinate system is quite arbitrary. Let's take the case of me lecturing in a classroom. So you all are sitting in front of me. You want to locate my position. So you take a coordinate system and you can place this coordinate system wherever you want. You can place this coordinate system on you and you can measure my position with respect to yourself. Or you can place the coordinate system on me. Now you can measure my position with respect to myself. Obviously that's going to be 0. Or alternatively, you can place this coordinate system on the fan which is fixed on the roof and measure my position with respect to this coordinate system. So basically the choice of the coordinate system is arbitrary. Now imagine that you measured the position vector of a charge in a particular coordinate system, and halfway through the problem you are going to switch to a new coordinate system. Now the question is, do you have to measure the new position vector again with respect to the new coordinate system, or can you write the position vector of the new coordinate system using the position vector of the old coordinate system? Now if you have to remeasure every time you make a switch of the coordinate system, this is going to cost you a lot of time. On the other hand, if you can write the new coordinate system using the old coordinate system, then that's going to save you a lot of time. So this is known as a vector transformation. So let's take a simple case. Assume that you have a coordinate system x, y, z, and vector A is written in terms of x, y, z components. Now you are going to rotate this coordinate system about the x-axis by an angle phi. So you have a new coordinate system now, x bar, y bar and z bar. Since you are rotating this about the x-axis, x bar is same as x. Now we want to represent the vector in the new coordinate system x bar, y bar, z bar. Let me call that as a bar. The question is, can I write a bar in terms of a? Or can I write ax bar, ay bar, az bar in terms of the old components ax, ay and az? So let's get the geometry right. The new coordinate system x bar, y bar, z bar are rotated with respect to the old coordinate system by an angle phi. Let theta be the angle of A with respect to y-axis and theta bar be the angle of A with respect to the new coordinate system y. So you can write ay as a cos theta and az as a sin theta. Similarly, you can write a y bar equal to a cos theta bar and theta bar equal to theta minus phi. So this is a cos theta minus phi. You can expand this and write a cos theta cos phi plus sin theta sin phi. Now a cos theta is ay, so this is cos phi ay plus sin phi az. Similarly, you can write a z bar equal to minus sin phi ay plus cos phi az. Now you can write this in the matrix form. So matrix ay bar az bar equal to cos phi sin phi minus sin phi cos phi multiplied by matrix ay az. So in general, The new component matrix Ax bar, Ay bar, Az bar can be written as an R matrix multiplied by the old component matrix Ax, Ay, Az. You can write this in a more compact form. So Ai bar equal to sum over j from 1 to 3 Rij Aj. So 1 represents the x component, 2 y components and 3 for the z component. For example, if you give the value of I as 1, so 1 is the x component, so Ax equal to Rx j from 1 to 3, so first component is Rxx Ax plus Rxy Ay plus Rxz Az. So this gives you the first row of this matrix multiplication. So this is how you transform vectors when you switch from one coordinate system to another coordinate system. And if you understand this, this is going to save you a lot of time while doing vector mathematics. So that's for today. In next class, we are going to discuss about differential calculus of vectors. Thank you.